So this is the second video of chapter 1. This will be on the photoelectric effect and the emission spectra of atoms. So when you shine a light, and EMR here symbolizes electromagnetic radiation. So light is an electromagnetic radiation. When you shine some light on some metals, electrons are dislodged, which produces an electrical current. So the light is able to give energy to those electrons and they are plucked out. If light behaved as a wave, the energy of light should be only dependent on the amplitude of light, which means the intensity of the light used for this to happen. And Einstein thought that shining red light or blue light of the same intensity on a metal would dislodge the same number of electrons, right? If light is a wave, then only the intensity would matter, not the fact that it's a red or a blue light. So let's look at this animation from Photon, Colorado to see what he observed. So I'm going to use this animation from Photon, Colorado about the photoelectric effect. So you see this lamp shining some light, and the light can be, all kinds of colors that are visible, up to infrared light, or if I go all the way here to the left, it's UV light. And the wavelength changes, right, depending on where this cursor is positioned. Let's start, just before violet light. The intensity of the lamp is at 100%. And here we have selected sodium as the metal. The metal here is where the light will shine. So let's start. And here we have some UV light at a wavelength of 372 nanometers. And we see that shining this UV light on the piece of sodium is able to pluck electrons out of the sodium. And this creates a current. You can see the value of the current here next to the what looks like a battery. Now, if I change the intensity of the light, I keep my wavelength and change the intensity to, let's say, 50%. If Einstein was right in his idea at the time, then I should not see any more, or I should see, I should not see photons or electrons being extracted, right? He said that it should only matter on the intensity, but you see that even if the intensity is low, we are able to extract electrons. And if I go even lower than that, 18%, we still are able to extract electrons. Less of them, but still we are able to extract electrons. So the intensity only affects the number of electrons you can extract, but it doesn't affect the ability of extracting electrons. So let's go back to 100% of intensity. Now, if I change the wavelength and I go into the violet, I'm still able to pluck electrons. I go into the blue, I'm still able to pluck electrons. Let's go into light blue. It still works. There seems to be less, but if you notice here, the current has decreased a lot, right? If I go back here, the current was 0.177. Now if I go back into, like, let's say the green, oh, the current is 0. Right now, very few electrons are plucked out of the sodium. And if I move into the yellow light is not able to pluck electron out of the sodium piece of metal. So you can see here that the wavelength really matters. It's gives the ability to pluck electrons or not. And knowing that a longer wavelength means less energy, a shorter wavelength means more energy. So looks like you need more energy to be able to extract those electrons. So what matters is more the wavelength and the energy of the light, more than its intensity that matters. So we can see that Einstein, when he thought that red light, blue light would not matter, but the intensity of the light would matter, it's not true. Actually, what he saw is that red light or blue light produced a different electrical current, right? We saw that blue light was able to provide some current, but red light, it stopped at actually the yellow light, and red light would not produce any electrons. So it did depend on the wavelength of the light, not its intensity. The intensity only made the amount of electrons more or less, but the ability to pluck electrons was dependent on the wavelength. So in conclusion, light could not be described as a wave because that doesn't correspond to the behavior of a wave. But if light instead behaved as a particle, then that would explain some of these results. And you can watch this other video here on the photoelectric effect if you have time here. It's Professor David who explains here. So scientists in the early 20th century showed that electromagnetic radiations was composed of particles that were called photons. So the main scientists who developed that theory were Max Planck and Albert Einstein. So those two scientists are the ones who started to think of light as photons. And so photons would be a particle of light energy, right? The amount of energy carried by a photon depends on the wavelength, right? We have this formula here. So capital E is the energy, H is the Planck constant, and nu, if you remember, nu is the frequency. So E, the energy of the photons, is equal to the constant, the Planck constant times the frequency nu. And since nu is C over lambda, lambda is the wavelength, then the energy can be written as H, the Planck constant, times C over lambda. C is the speed of light, the celerity of light, and lambda is the wavelength. So we can see that the energy of the photon would depend on the wavelength. So we can say now that the electromagnetic radiation, which is light, can exhibit both wave and particle behavior. And so we say that it has a wave-particle duality. So what it means is that sometimes to understand what's going on when you have light involved, you can see it as a wave, and that explains some things. But sometimes you need to see light as photons and particles to understand, the effect of light. So it can be seen as both. Of course, depending on the problem you are looking at, it will be easier to choose one or the other of the way of seeing light. So light as a wave or light as a stream of photons. And so if we look at this formula, E equals hc over lambda, we can see that if lambda is small, so if we have a short wavelength, then the energy will be larger, right? Because lambda is in the denominator, so it makes the energy larger if lambda is small. So a short wavelength will imply a high energy. So here you see the blue color, the blue light has a shorter wavelength, and so it's represented with bigger photons, right? The balls here represent the photons, and so it's bigger than for the red light. And if you have a high frequency light, then the photons will have a high energy too. And the high frequency means short wavelengths, right? And because of the formula E equals h nu, if nu, the frequency is large, then the energy will be large. So high frequency means high energy. So that's why the ultraviolet light has a higher energy than the infrared or red light. And so if we look at, if you remember the emission spectrum of the light, of all electromagnetic radiations, the radio waves, photons have the lowest energy because they have the longest wavelength, and the gamma rays have the highest energy because they have the shortest wavelengths. So high energy electromagnetic radiation can potentially damage biological molecules, right? Because they are high energy. And they can really damage the atoms. We can see with the example of the sodium that ultraviolet light or violet light had the effect of plucking electrons out of the sodium. So high energy electromagnetic waves can ionize the atoms, and that can cause ionizing radiation in biological molecules. So that's why you have to protect yourself from UV light, for example. So here you have the emission spectra of, or emission spectrum of all electromagnetic radiations. And so among them, there is the microwaves, the gamma rays, green light, red light, or ultraviolet light. And we ask you in this concepts check to order these specific electromagnetic radiations order them by wavelengths from short to long, by frequency from low to high, and by energy from least to most. So I want you to pause the video so you can work on this on your own before you watch the answer. As always, the best way to learn is to try to remember and do the work yourself. So let's do this. If we have to order them by wavelengths from short to long, so which one would be the shortest wavelengths among the microwaves, gamma rays, green light, red light, ultraviolet light? Here in the spectrum you have the wavelengths given in meters, and we can see the radio waves have very large wavelengths, so that will be on the long side. And then gamma rays are the ones that are the shortest. So let's start by writing here gamma rays would be the shortest. And then after that, we need to classify green light, red light, UV light. Ultraviolet is symbolized by UV, and UV comes before the visible light. So UV is there. It's shorter than longer than gamma rays, but still on the short side. Then comes the green light, then the red light, and then the microwaves. So when ordered by wavelength from short to long, that's how you would order them. Oops, I miss so green, red, and microwaves. Okay, let's order them by frequency now. So frequency is varying in inverse relationship to the wavelength. So when you have a short wavelength, you have a high frequency, right? You remember how they are inversely related. So if the gamma rays have a short wavelength, then they will have a high frequency. So they will be at the end of the scale here. And if microwaves have long wavelengths, then they will have a short frequency or low frequency. So from low frequency to high frequency, then we would start with the microwaves. They have low frequency because they are the longest wavelengths. Then comes the red light, then green light, then UV, and gamma rays. So ordered by frequency, that's how it looks like. Microwaves have a low frequency. Red, green, UV, and gamma rays are the highest in frequency. Now let's order them by energy. So energy is proportional to frequency because of E equals h nu. Nu is the frequency, so you can see that energy is proportional to the frequency. So if we need to order by energy from the least to the most, then we can use just the same ordering as above for frequency. Microwaves with low frequency will have a low energy, then red light, then green light, then UV light, then gamma rays. Gamma rays will have the most energy because they have the highest frequency and the shortest wavelengths. Sorry. So let's continue here. Light's relationship to matter. So atoms can acquire extra energy. So if you bring energy from the outside and bombard the atoms with it, they can absorb that energy. And in the illustration here, we have, so be careful, the atoms are the blue spheres, right? The blue spheres here represent hydrogen atoms. You can excite them by shooting energy to them, and they will absorb that energy and become excited. When we talk about an atom being excited, it means it has more energy than in its ground state. So here those hydrogens with the little red waves symbolize the fact that they have more energy, they are excited. But eventually they must release that energy. They cannot stay in an excited state for too long. And when atom emits energy or release it, it's usually released in the form of light. And we can see here in the second drawing that the excited atoms will emit photons of light. And by emitting the photons of light, the energy will be gone and they will return to their ground state, right? The arrows showing the photons means that the energy leaves the atoms and is emitted in the form of light. So that means atoms can emit light. They can emit light. However, atoms don't emit all colors of the spectrum. They are not like white light with all the wavelengths in there. No, they only emit very specific wavelengths. In fact, the spectrum of wavelengths that they emit can be used to identify the elements. Because here you see a picture showing solutions of metal cations in ethanol, probably. And if you burn those solutions that contain the metal ions, they will emit, the flame will have these different colors, right? They are very distinct colors. And we know now that white light can be due to magnesium or aluminum. Red light can be due to lithium or strontium. Yellow light is due to sodium. Green light can be copper. And then blue light, again copper or some other elements. So these colors are allowing chemists to actually know what kind of ions they have in a solution. And so the emission spectra, for example, for the hydrogen atom looks like this. And it's not called a continuous spectrum like we had earlier with the electromagnetic radiation, right? This is called a line spectrum of hydrogen. Line, as opposed to continuous, means it only emits light at certain wavelengths, right? There are only certain energy levels that the hydrogen atom is allowed to move between. And we call these a quantized energy level. Quantized means that the atom could only have very specific amounts of energy, right? It can only absorb specific amounts of energy. And when it's going from the excited state back to the ground state, the photons that are released will emit light in very specific wavelengths, which means with very specific amount of energy, right? So here the line spectrum for hydrogen has only 4 emissions in the visible. So these are visible colors. 410 nanometers is violet, then there is a blue line and a green, and then the orange red line here. So that's the only colors that hydrogen can emit. And in between it's black. It doesn't emit anything. These are other examples of line spectra for different atoms. So each atom has a specific line spectrum. The top one is for neon. So neon only emits mainly in the red, yellow and green. And there's only one line in the violet there. So by looking at these line spectra, you can identify atoms also. Notice how iron here emits in a much wider range of wavelengths, right? There's much more lines, a lot in the violet and blue, then more in the green, some in yellow, and then some in the red. So these line spectra are allowing chemists to identify elements.